There is a story we have been telling ourselves for a very long time, a story whispered through the corridors of science fiction, painted across cinema screens in brilliant light, and pressed into the pages of novels that have shaped how entire generations imagine the future of intelligent life in this cosmos. It is a story of sleek vessels cutting silently through the dark between stars, of civilizations so advanced they have learned to bend space itself to their will, of beings who look up at the night sky and see not an impassable ocean of void, but simply a neighborhood, a familiar and navigable geography of worlds waiting to be visited and mapped and shared. It is, at its core, a story about a universe that is fundamentally hospitable to life that wants to move through it. And it is, at its core, a story that is physically wrong. Not wrong in the casual sense that we have simply not yet built the right engines or discovered the right fuel source. Not wrong in the optimistic sense that perhaps a few more centuries of technological refinement will unlock the secrets that currently confine us. Wrong in a far more absolute and beautiful and devastating sense. Wrong in the sense that the very geometry of reality, the precise curvature of space-time itself, has already written the conclusion to this story in the cold, indifferent language of mathematics, and that conclusion does not include galactic federations or interstellar empires or the warm handshake of species from distant solar systems finally making contact across the void. The universe is not hostile to intelligent life in the way a predator is hostile to its prey. It is something far more elegant and far more final than that. The universe is geometrically indifferent, and gravity, the force we experience as the most mundane and familiar presence in our daily lives, the thing that keeps our coffee in our cups and our feet on the ground and the moon faithfully circling overhead, is the precise mathematical instrument through which this indifference expresses itself as an absolute, inescapable, and permanent physical barrier. To understand why, we need to abandon the comfortable framework of gravity as a force, the old Newtonian image of an invisible hand reaching across space and pulling massive objects toward one another. That picture, while useful for calculating the arc of a thrown ball or the orbit of a satellite, conceals the true nature of what is actually happening in the deep structure of physical reality. Albert Einstein revealed something far stranger and far more consequential. Gravity is not a force at all. Gravity is geometry. Gravity is the curvature of space-time itself, the way the presence of mass and energy bends and warps the four-dimensional fabric of the universe, creating shapes in that fabric that all other objects, including light itself, must follow as they move through it. Imagine stretching a perfectly smooth, perfectly taut elastic membrane across an enormous frame, a surface so uniform and so precisely tensioned that it is, for all practical purposes, a flawless mathematical plane extending in every direction. Now, place a bowling ball at the center of that membrane. Watch what happens. The surface does not remain flat. The mass of the bowling ball curves the membrane downward beneath it, creating a deep, sweeping depression that spreads outward in all directions, a bowl whose walls grow steeper and more dramatic the closer you approach the center, and whose edges fade gradually into the surrounding flat geometry of the undisturbed membrane far from the ball. Now place a marble on that membrane somewhere near the edge of the depression and release it. The marble does not travel in a straight line. It cannot. The geometry of the surface it is moving across has already determined its path. It follows the curve. It spirals inward toward the depression, not because some invisible hand is pulling it, but because the straightest possible path through that curved surface happens to lead downward toward the center along the slope that the massive bowling ball has carved into the fabric of the membrane simply by existing. This is general relativity. This is gravity. And the bowling ball in this picture is not a bowling ball at all. It is every planet, every star, every black hole, every dense clustering of matter that exists anywhere in the observable universe. Each of them is carving its own depression into the fabric of space-time, its own gravitational well, its own inescapable geometric sinkhole in the smooth surface of reality. And everything that exists in the universe, every particle of matter, every photon of light, every spacecraft any civilization has ever built or imagined building, must navigate across this landscape of curves and wells and slopes, following the geometry that mass has already written into the structure of space and time. Now consider the civilizations we imagine inhabiting distant star systems. Picture a world orbiting a star, not entirely unlike our own sun, a rocky planet with liquid water and a dense atmosphere, and the full chemical complexity required to produce not just life but intelligence, technology, the capacity to look up at the night sky and wonder what lies beyond. This civilization has developed. It has mastered chemistry and then physics and then engineering. It has built machines and cities, and eventually, inevitably, it has turned its attention to the stars. It wants to leave. It wants to cross the void. It wants to find us or others like us, or simply to expand beyond the gravitational embrace of the star that gave it life. And here is where the geometry of reality delivers its first and most devastating verdict. That civilization lives at the bottom of a gravitational well, not metaphorically, precisely. Their planet, orbiting their star, is embedded in a curvature of space-time so deep and so steep that simply lifting a significant mass off the surface of that planet and sending it upward, away from the planet and eventually away from the star system itself, requires an amount of energy that is not merely large but is staggering in a way that resists easy comprehension. Consider our own situation as a concrete illustration of the mathematics at work. Earth's gravitational potential well is defined by a quantity called escape velocity, the minimum speed an object must reach to break free from Earth's gravitational geometry and not fall back. That number is approximately 11.2 kilometers per second. To achieve that speed, every kilogram of mass you want to lift off the surface and send into space requires a precisely calculable amount of kinetic energy. For a single kilogram, that energy is approximately 63 million joules. For 1,000 kilograms, 63 billion joules. For a spacecraft massive enough to carry the life support systems, fuel reserves, radiation shielding, scientific equipment, and structural integrity required for a genuine interstellar journey, a spacecraft that might weigh several million kilograms just at the outset, the energy demand from Earth's gravity alone climbs into numbers that begin to strain the vocabulary of enormity. But escaping Earth's gravity is only the first step, and it is the smallest step in the sequence. Because our planet orbits the sun, and the sun has carved a gravitational well into spacetime that is far deeper and far more demanding than Earth's. To escape the sun's gravitational geometry entirely, to actually leave the solar system rather than simply falling into an orbit around our star at some different altitude, a spacecraft must reach an escape velocity from the sun's gravitational field of approximately 617 kilometers per second at the distance of Earth's orbit. The energy demand scales accordingly. To send a meaningful mass, a vessel heavy enough to actually sustain a crew or carry the necessary technology for genuine interstellar operations, out of the sun's gravitational well requires harvesting an amount of energy that dwarfs everything humanity has ever produced across the entirety of its industrial history. And this is precisely the arithmetic that dismantles the fantasy of interstellar civilizations. The energy required does not scale gently with mass, it scales brutally. The relationship between the mass of your spacecraft and the energy required to lift it out of a gravitational well is not forgiving. Every additional kilogram of shielding you add to protect against interstellar radiation requires more fuel to accelerate. Every additional kilogram of fuel you add to carry that shielding requires yet more fuel to accelerate the fuel. This is the tyranny of the rocket equation, a mathematical relationship so merciless that engineers refer to it with genuine reverence, because it has an absolute quality to it that no amount of clever engineering can fundamentally escape. You cannot trick the rocket equation. You cannot negotiate with the geometry of space-time. The numbers for a true interstellar mission are not merely challenging. They are civilization scale in their demand. Studies of the physics of interstellar travel consistently arrive at the same uncomfortable conclusion. To send a vessel of any meaningful mass to even the nearest star system, Alpha Centauri, at approximately 4 light-years distance, within a time frame short enough to be meaningful, requires energy equivalent to many years of total energy production by the entire human civilization on Earth. For a vessel large enough to carry the systems required for a genuine interstellar mission, the energy requirement climbs toward the total energy output of our sun across years or decades of continuous burning. This is not a problem of insufficient ambition. This is not a problem that more advanced technology will eventually solve. This is a problem written directly into the mathematics of space-time geometry by the structure of general relativity. The gravitational well of a star is not a technological obstacle. It is a geometric fact. And the energy required to climb out of it is not a parameter that shifts as technology improves. The energy cost of lifting mass against gravitational curvature is fixed by the geometry of the well, by the mass of the star creating it, by the depth of the depression it has carved into space-time. No technology can reduce that cost. The most any technology can do is convert fuel into thrust more efficiently, but the fundamental energy requirement remains anchored to the mathematics. Now consider that every civilization in the galaxy faces this precise mathematical reality. Every intelligent species that has ever evolved on a rocky world orbiting a stellar furnace lives at the bottom of a layered gravitational prison, their planets well nested within their stars well nested within the collective gravitational influence of whatever galactic structure surrounds them. The geometry that confines them is not a temporary obstacle awaiting a sufficiently clever solution. It is the permanent, precise architecture of the universe they inhabit. We move now from the energy economics of gravitational wells to something even more sobering, even more beautiful in its cold mathematical ruthlessness. The second profound truth that gravity delivers against the fantasy of interstellar civilization concerns not merely the energy required to leave a star system, but what happens to any vessel brave or foolish enough to attempt navigating through the gravitational landscape that lies between star systems. Because the space between stars is not empty in any simple sense. It is a landscape, a complex and violent three-dimensional terrain of gravitational curvature, shaped by the collective mass of every stellar object in the galaxy, by the dense concentration of matter at the galactic center, by the invisible but physically real influence of dark matter distributed throughout the galactic structure, by the intense gravitational field surrounding the remnants of dead stars, neutron stars and black holes and white dwarfs scattered across the interstellar medium like debris from the universe's most catastrophic engineering failures. To navigate this landscape is not like navigating open ocean on a calm day. It is like attempting to thread a path through a three-dimensional maze of invisible whirlpools, some of them merely disruptive, others absolutely lethal, none of them marked, all of them defined by the curvature of space-time that their masses have carved into the fabric of reality. And the effects of this curved landscape on a traveling vessel are not merely inconvenient. At the scales of mass and velocity required for genuine interstellar travel, they are physically catastrophic. Consider what happens in the vicinity of a neutron star, one of the most extreme concentrations of mass the universe produces from the death of ordinary stellar matter. A neutron star may contain more mass than our own sun, compressed into a sphere perhaps 20 kilometers across. The gravitational curvature around such an object is so extreme that the difference in gravitational field strength between one side of a spacecraft and the other, even at distances of thousands of kilometers, is enormous by the standards of material physics. This differential in gravitational pull, what physicists call tidal forces, is not a gentle gradient. It is the difference between the gravitational acceleration experienced by the near edge of your vessel and the gravitational acceleration experienced by the far edge, and for a neutron star at close range, this difference is so vast that it would exert enough force to stretch any conceivable material structure, any metal, any composite, any material that atomic physics permits us to construct, well beyond its breaking point. The technical term for what happens to matter subjected to this kind of differential gravitational force is spaghettification. And while the word sounds almost playful, the physical reality it describes is the complete atomic disassembly of whatever structure is being stretched. The tidal forces do not merely damage a spacecraft, they overcome the electromagnetic forces binding its constituent atoms into solid structures. They pull the vessel apart at the most fundamental level of material physics, converting it from a structured object into a stream of particles following different geodesics through the curved space-time geometry. And neutron stars are not the most extreme gravitational objects a hypothetical interstellar traveler would need to navigate around. Black holes, the ultimate expression of gravitational geometry in the universe, represent regions where the curvature of spacetime has become so extreme that the mathematics of general relativity predicts not merely a steep gravitational well, but a complete topological break, a region where the curvature becomes infinite, and where the escape velocity exceeds the speed of light. Nothing that enters the event horizon of a black hole returns. Not light, not information, not, certainly, any spacecraft. But the danger of black holes for interstellar navigation extends far beyond the event horizon itself. The region of space surrounding a black hole, the accretion disk of superheated matter spiraling inward, the intense jets of radiation and particles ejected perpendicular to the disk at relativistic speeds, the extreme tidal forces extending outward from the central singularity for enormous distances, creates an environment in which navigating anywhere near the object requires confronting a gauntlet of physical forces that dwarf anything the engineering of even the most optimistic science fiction scenario could withstand. And black holes are not rare curiosities at the edges of the observable universe. They are distributed throughout every galaxy, including our own Milky Way. At the center of our galaxy sits Sagittarius A star, a supermassive black hole containing approximately 4 million solar masses, carving a gravitational depression into spacetime so vast and so deep that it shapes the orbital dynamics of stars across a region spanning thousands of light years. Any civilization attempting to navigate toward the galactic center or to use the gravitational geometry of the galactic core as a shortcut through the galaxy would be flying into an environment defined by some of the most extreme space-time curvature outside of the Big Bang itself. But there is a subtler effect of traveling through the curved space-time landscape of the galaxy that does not require proximity to any extreme gravitational object, an effect that operates continuously and universally on any massive object moving through the universe. And this brings us to the third profound truth that gravity delivers against the possibility of interstellar civilization. When you move a massive object through space, you do not simply translate it from one location to another without any physical consequence to the surrounding universe. The mathematics of general relativity makes a precise and unavoidable prediction. Accelerating massive objects through space-time creates disturbances in the fabric of that space-time, ripples that propagate outward at the speed of light, carrying energy away from the accelerating mass and distributing it through the surrounding medium of space-time itself. These ripples are gravitational waves, and they are not merely a theoretical curiosity. They are a physically real and experimentally confirmed phenomenon that represents an absolute and inescapable consequence of moving massive structures through the universe. The detection of gravitational waves by the LIGO Observatory beginning in 2015 confirmed what general relativity had predicted for a century. When massive objects accelerate, they radiate gravitational waves. The systems that LIGO detected, pairs of black holes and neutron stars spiraling toward each other and merging in cataclysmic collisions, lost enormous amounts of energy to gravitational wave radiation during their in-spiral. In the final moments before merger, these systems were radiating more power in gravitational waves than the entire observable universe produces in light from all its stars combined. The energy lost to gravitational radiation is real, it is measurable, and it operates according to mathematics that depends on the mass of the accelerating objects and the rate at which they are accelerating. For the scenario of an interstellar spacecraft, the gravitational wave power radiated by the accelerating vessel is, for any mass and acceleration achievable by engineering, absolutely minuscule compared to the energy output of the propulsion system. This is a genuine physical truth, and it must be stated precisely. A spacecraft of the kind discussed in optimistic interstellar travel scenarios does not lose meaningful amounts of energy to gravitational wave radiation during its journey. The gravitational wave power for such systems is many orders of magnitude below the scale of any practical engineering concern. But this is not the end of the story that gravitational radiation tells about the impossibility of interstellar civilizations, because the question is not merely whether a single spacecraft loses energy to gravitational waves. The question is what it means to build and operate the energy infrastructure required to launch and sustain interstellar travel at civilizational scale, and what the physics of gravitational radiation tells us about the fundamental energy economy of the universe. Consider what genuinely massive astronomical accelerations, the kinds of mass movements that would be involved in true civilizational scale attempts to modify gravitational geometry or harness the energy of entire stellar systems, actually radiate in gravitational waves. Binary star systems, pairs of massive stars orbiting each other, radiate gravitational waves continuously and lose orbital energy at a rate that causes them to spiral slowly inward toward each other over astronomical timescales. The famous Hulse-Taylor binary pulsar, a pair of neutron stars discovered in 1974, has been observed to be losing orbital energy at a rate that matches the predictions of general relativity for gravitational wave emission to extraordinary precision. The universe is continuously, inevitably, and precisely draining energy from massive orbiting systems through gravitational radiation. Any civilization contemplating the manipulation of gravitational fields or the construction of Dyson sphere-scale energy harvesting structures, the kinds of projects that science fiction imagines as precursors to interstellar travel capability, would be operating at scales where the physics of gravitational radiation becomes not merely a theoretical consideration but a genuine and unavoidable energy drain on their projects. More fundamentally, they would be operating in a universe where every attempt to do work on massive scales, to accelerate mass, to change the orbital dynamics of large objects, to harness the gravitational energy of their star or planetary system, generates gravitational wave radiation that carries real energy away from the system and deposits it irretrievably into the fabric of spacetime. The universe does not offer free lunches in its energy economy. Every massive process pays a gravitational radiation tax on its transactions, and while the individual rates may be small, the principle they represent is absolute. You cannot accelerate mass through spacetime without disturbing spacetime. You cannot disturb spacetime without radiating energy. And you cannot recover that radiated energy because gravitational waves propagate at the speed of light in all directions simultaneously, spreading their energy across an ever-expanding sphere of spacetime that cannot be recalled or recaptured. The energy is gone, dissolved into the geometry of the universe, as permanent and as irrecoverable as the heat death toward which thermodynamics is slowly but precisely driving all physical processes. There is something that must be confronted directly at this point in our examination of gravity as the ultimate cosmic quarantine. And that is the suite of theoretical proposals that science fiction and occasionally serious physics papers have advanced as potential escape routes from the gravitational confinement we have been describing. Warp drives, wormholes, exotic matter configurations, the manipulation of space-time geometry through engineering rather than through the crude mechanics of thrust and mass ejection. Do not these theoretical possibilities represent genuine loopholes in the geometric prison we have been describing? The honest answer requires both intellectual humility about what we do not know and intellectual precision about what the mathematics of general relativity actually permits. The Alcubierre metric, proposed by physicist Miguel Alcubierre in 1994, is a genuine solution to Einstein's field equations that describes a space-time geometry in which a bubble of flat space is surrounded by a region of contracted space ahead and expanded space behind, allowing the bubble and anything inside it to effectively travel at superluminal speed relative to distant observers without any local violation of the speed of light. It is mathematically legitimate, and it is physically realizable under precisely one condition: the existence of matter with negative energy density, what physicists call exotic matter, in quantities that current estimates suggest would need to exceed the total mass energy content of a planet or more. Exotic matter with negative energy density has never been observed. There is no evidence that it exists in the universe. And the quantum inequalities that govern energy distributions in quantum field theory place extremely severe constraints on how much negative energy density can exist in any region of space and for how long. The wormhole scenario is similarly constrained. General relativity permits solutions to its field equations that describe topological shortcuts through spacetime, tunnels connecting distant regions of the universe through a geometry that bypasses the intervening space. But stabilizing such a structure against immediate gravitational collapse requires, again, Exotic matter with negative energy density in quantities that appear to be physically unrealizable, given everything we currently understand about quantum field theory and the energy conditions that real physical matter must satisfy. The mathematics permits wormholes in the abstract space of solutions to Einstein's equations. The physics of actual matter in the actual universe appears to forbid their physical realization. We are left, then, with a universe in which the geometry of spacetime is not an obstacle to be engineered around, but a fundamental and unyielding feature of physical reality. The gravitational wells of stars and planets are not engineering problems awaiting sufficiently clever solutions. They are precise consequences of the distribution of mass and energy in the cosmos, described by equations that have been tested to extraordinary precision and found to accurately describe the behavior of reality at every scale, from laboratory experiments to the dynamics of galaxy clusters. These equations do not contain escape clauses. They do not get easier to satisfy as technology advances. They describe a cosmos in which gravity is not a force to be mastered, but a geometry to be inhabited. Now, let us step back from the cold mathematics for a moment and see the full picture that is emerging from all of this, because there is something genuinely profound in what the physics is telling us, something that goes beyond the merely negative conclusion that interstellar travel is extraordinarily difficult. The physics is telling us something about the structure of the universe at the deepest level. It is telling us about the relationship between mass and space and time and energy that Einstein's equations encode. And what they encode, when you trace the implications far enough, is a universe that is geometrically organized into local islands of stability, each gravitational well defining a region of space-time where a civilization can persist and develop and build complexity, surrounded by vast stretches of hostile, energetically inaccessible void. Consider the structure of the Milky Way galaxy as a physical system. It is a disk of approximately 200 to 400 billion stars, spanning roughly 100,000 light-years in diameter, with a supermassive black hole at its center, and a distribution of dark matter extending well beyond the visible stellar disk. The stars within this disk are not uniformly distributed. They are concentrated in spiral arms and moving in complex orbital patterns around the galactic center, but the average distance between neighboring star systems is approximately 4 light-years. That distance is not arbitrary. It reflects the gravitational dynamics of how star formation distributes mass through a molecular cloud, how the balance of gravitational attraction and thermal pressure determines where stars condense and how far apart they settle. The structure of the galaxy is itself a product of the same gravitational physics that prevents any civilization within it from easily crossing the spaces between systems. The average separation of 4 light-years between stellar neighbors translates, at the speeds achievable by any propulsion system that does not invoke physically unrealizable exotic matter, into journey times measured in thousands to tens of thousands of years, not centuries, not decades. Geological timescales. The timescale over which our species rose from its earliest ancestors to the launch of our first satellites, the timescale over which civilizations rise and collapse and transform into something unrecognizable to their origins. To travel between star systems at any speed achievable without exotic physics is to commit to a journey that spans the equivalent of human recorded history multiple times over, with no guarantee of arrival and no possibility of return, within any continuous social or cultural context that could give the journey meaning. And this is assuming you can harvest enough energy to escape the gravitational well of your home system in the first place. Here is the picture that assembles itself from these physical realities. Across the galaxy and across every galaxy in the observable universe, there may be enormous numbers of planets that have developed life. The chemistry of carbon and water is not rare. The conditions for the emergence of biological complexity, while requiring certain specific parameters of planetary physics and stellar environment, are not so restrictive that the universe would produce them only once. There may be thousands, millions, perhaps billions of worlds where evolution has run its patient course and produced something that looks up at the night sky and wonders. And every single one of those civilizations, regardless of how ancient and how technologically sophisticated they have become, faces the identical mathematical reality we have been examining. They are at the bottom of a gravitational well. The well was carved into spacetime by the mass of their star and their planet. The walls of the well are defined by the field equations of general relativity, equations that do not yield to technological progress or civilizational ambition. The energy required to climb those walls exceeds the energy budget of any civilization that has not discovered physically realizable ways to violate or bypass the constraints of known physics. And the evidence, from the precision of our measurements of physical constants and the extraordinary accuracy of quantum field theory and general relativity across every scale we have tested them, suggests that the known physics is not wrong in any way that would open the doors that currently appear to be closed. Each civilization is an island, not metaphorically. The gravitational geometry of their star system is a precise and measurable physical boundary around their local region of spacetime, within which they can operate freely and beyond which the energy economics become catastrophically prohibitive. The distances between these islands are measured in light years. The travel times between them at achievable speeds are measured in millennia, and the gravitational landscape between them is a gauntlet of curved spacetime that would physically disassemble any sufficiently massive structure attempting to navigate it at the required velocities. This is why the night sky is silent, not because life is rare, not because civilizations inevitably destroy themselves before they can reach the stars, not because we are somehow special or unique in a universe that has been running the experiment of stellar and planetary formation for 13.8 billion years. The night sky is silent because gravity has organized the universe into a collection of local environments separated by vast, energetically hostile spaces, and the mathematics of that organization is indifferent to the wishes of any species that has evolved within one of those environments and learned to want more than its gravitational well can easily permit. There is a chilling elegance to this conclusion that deserves to be felt fully rather than immediately deflected into optimistic speculation about future technologies. The same force that made our planet habitable, that holds the atmosphere we breathe against the surface of the Earth, that keeps the liquid water oceans from boiling away into space, that maintains the stable orbital dynamics of the moon, that moderates our climate, that powers the nuclear fusion in the sun, that drives the energy cycles sustaining all biological life on our world. This same force is the precise geometric mechanism that ensures we will remain local, that our presence in the cosmos will remain bounded by the curvature of the space-time region we inhabit. Gravity gives and gravity confines with the same mathematical precision, the same equations, the same field of curvature. The gift and the prison are identical. They are the same geometry viewed from different perspectives. The perspective of a creature that needs planetary conditions to survive, and the perspective of a creature that wants to escape those conditions and travel to other stars. There is a quality to the universe that this physical picture reveals, a quality that goes beyond the merely prohibitive and touches something deeper in our understanding of what kind of place the cosmos actually is. We have inherited from the early decades of the space age and from the cultural imagination that space exploration ignited a sense that the universe is fundamentally open, that the stars are destinations rather than background, that the direction of complexity and intelligence in the cosmos is outward and expansive, and that the story of any sufficiently advanced civilization is necessarily a story of spreading beyond its origin world into an ever larger sphere of inhabited space. The physics suggests a different story. The physics suggests that the direction of complexity is not primarily outward but inward, not spatial expansion but depth, the increasing sophistication of what can be built and known and experienced within the bounds of a single gravitational island. A civilization confined to a single star system by the geometry of space-time is not a civilization that has failed to become interstellar. It is a civilization that has been given, by the precise mathematics of the universe it inhabits, an extraordinarily complex and rich local environment and an essentially unlimited timescale within which to explore that environment. A single star system contains more complexity, more physical variety, more chemical richness, more orbital dynamics and planetary diversity, and potential for engineering and art and science and the inner life of minds than any civilization has yet come close to fully understanding or utilizing. The observable universe is thought to contain somewhere between 200 billion and 2 trillion galaxies. Each galaxy contains billions to hundreds of billions of stars. Each star potentially hosts planetary systems of enormous variety. The number of local gravitational islands in the observable universe is a number so large that it sits outside normal human intuition, a number that makes even the largest quantities we use in everyday life look microscopic by comparison. And in each of those islands, the same geometry that prevents crossing the void between them is simultaneously creating the conditions for profound physical and potentially biological complexity within them. The universe is not a network of destinations connected by navigable routes. It is a collection of isolated experiments in local physics, each one contained within its own gravitational boundary, each one developing whatever it develops in conditions that are defined by the specific mass distribution and stellar environment of that particular island of space-time. What happens in each of these islands stays, for all practical and most theoretical purposes, within that island. The geometry does not transmit civilizations across the void. It transmits light and gravitational waves and the electromagnetic signals we call radio waves, all of which travel at the speed of light, and all of which, by the time they arrive at another island, are so diluted by the inverse square law as to be nearly undetectable against the background noise of the cosmos. We send radio signals into the sky and they spread outward in all directions simultaneously, their power falling as the square of the distance, becoming quieter with every light year they travel, requiring receiving antennas of staggering size to detect even a relatively nearby transmission. After 50 light years of travel, our most powerful television broadcasts have become weaker than the natural radio background of the galaxy. After 1,000 light years, they are functionally undetectable by any receiving technology we can currently imagine building. And the nearest stars with any significant probability of hosting complex life are measured in hundreds to thousands of light years in some estimates. We are whispering into a vast and curved space, and the geometry that curves that space absorbs and dilutes our whispers before they can reach any ears that might be listening. There is a thought experiment that clarifies the deep structure of what the physics is revealing. Imagine standing at the bottom of a canyon so deep that the walls disappear into darkness above you in every direction. You can see the walls of the canyon in detail near the bottom where you stand. You can examine the rock, measure its composition, study its striations, understand its history. You can build extraordinary things within the space you inhabit at the bottom of the canyon. You can develop a complete and sophisticated understanding of the physics of the canyon itself. But you cannot see what lies beyond the rim without the equivalent of more energy than you can easily accumulate, more capacity for vertical movement than the geometry of the canyon walls permits. Every civilization in the galaxy is at the bottom of that canyon. Their version of the canyon is the gravitational well of their star system, carved into space-time by the mass of their star according to the precise equations of general relativity. And the rim of the canyon is not a fixed physical barrier they might eventually chip away at or climb over. The rim is defined by mathematics. The energy required to reach it is set by the mass of the star and the mass of whatever vessel they want to send upward. And the space beyond the rim, rather than opening into accessible countryside, opens into the gravitational landscape between star systems, a landscape of curves and tidal forces, and energetic hostility that makes the canyon itself look hospitable. The question then is not why we have not been visited. The question is how we could have ever expected to be visited, given what the physics of the universe we actually inhabit tells us about the energetic and geometric structure of that universe. The answer to the Fermi paradox, the famous puzzle of why a galaxy old enough and large enough to have produced many intelligent civilizations appears to have produced no visitors or obvious signals, is not a mystery requiring exotic explanations. It is the expected consequence of living in a universe governed by general relativity, in which the geometry of spacetime has organized matter into gravitational islands separated by chasms that the mathematics of energy and mass and curvature makes essentially uncrossable. The chilling silence of the cosmos is not an anomaly, it is a prediction. It is what general relativity would lead us to expect if we took its equations seriously enough and applied them not just to the motion of planets and the bending of light, but to the full civilizational implications of the universe. describes. The equations describe a universe of extraordinary local richness and vast interstellar separation, a universe where complexity can emerge and flourish within gravitational islands, and where the geometry that created those islands simultaneously ensures that they remain islands bounded by the precise curvature of their local spacetime and separated by distances that the same physics renders uncrossable without energy inputs that exceed what any bounded civilization can sustainably produce. We are here, on this particular gravitational island, looking outward at the curved geometry of our universe, and the profound mathematical reality is not a source of despair, but of something more complex and more honest. The universe that confinement reveals is one of genuine and overwhelming richness at the local scale. The physics of our solar system alone, the orbital mechanics of 8 planets and hundreds of thousands of smaller bodies, the plasma dynamics of our star, the chemistry of a planet that has been running complex self-organizing processes for 4 billion years, the quantum mechanics of the matter we are made from, and the materials we can build with, contains more depth and complexity than any civilization has yet fully mapped or understood. The curvature of space-time that keeps us here is the same curvature that made here worth inhabiting. The geometry that confines is the geometry that created. And in the precise, cold, beautiful mathematics of that geometry, in the field equations that describe how mass and energy shape the fabric of space and time, there is a kind of profound architecture that does not require us to imagine it as something other than what it is. It is not a cage built by an indifferent cosmos to frustrate the aspirations of intelligent life. It is the deep